Okay, hi, Math 2504. It is October 1st now, and this baby is due on October 20th. So here's project 2, discrete event simulation of an unreliable queuing network. In contrast to project 1 that dealt with polynomials, very interesting but static. This and deterministic. This type of thing is dynamic and stochastic, and you're going to make it, program it, program it, and it will move, it will run. All right, make sure you get a partner that you can work with and work well with your partner and get cracking. So there's a whole bunch of submission information here, and that's all nice and good. There's also information about the perspective seminar. This is not bonus, so this is part of the actual project. And the great thing is that Dr. Anna Foglin is actually a professional in this field of simulation. So there's some connection there. So let me describe the model that you will make a simulation for, okay? And this is the key thing about this video. So there's a lot of text here. The purpose of the video is to demystify this text. You don't need to look elsewhere for sources about this model or anything like that. It should all be here, and I hope this video will help. So what you're going to do is you're going to do a discrete event simulation. You'll learn what that is very quickly in the lectures. It's a simulation of time, and discrete event means it's continuous time, but things jump, time jumps from event to event, of an open generalized Jackson network with breakdowns. So what is that? Well, Jackson networks, they're well studied in applied probability and in stochastic modeling. The phrase generalized means that they also have non-exponential processing time. The phrase open means that jobs come from outside of the system. I'll explain what that is in a second. And breakdowns, well, servers can break down or not, okay? So this type of thing, you can think of it as some abstract simulation of maybe something like an amusement park, like maybe Dream World or one of those places. So the main idea is that you have capital L, maybe 5 or maybe 100, some finite fixed number of servers. Stations, servers are synonymous. You can also call them nodes, okay? So each one is, say, like a ride or some point of maybe a coffee stand as well, right? In Dream World, okay, or in your system. And customers, which you can also call jobs, move between these nodes. They come from the outside world, and then they move between the nodes, but they only leave a node after they receive service. So when they get to the node, they stand in line very nicely. They stand in queue, okay, or in the buffer. And they are served one by one, okay, not in batches in this case, just one by one. And when they finish with their service, they then go elsewhere. And I'll explain the mechanism for going elsewhere. It's going to be kind of a random mechanism of going elsewhere, but there's also a random mechanism of arrival and a random mechanism of service. Okay. And the other component is that there are also breakdowns in the system. So servers change between on and off. Okay. So a job or a customer, if you would like, can be, where can a job be? It can be out of the system. That means it still hasn't arrived, or it has left, and then it's gone. We're done with it. Or it can be in the system, in a buffer, i.e. a queue of one of the stations or nodes. Okay, the station is a node, and it's waiting in the queue. Okay, so it's standing in the queue. There are other jobs in front of it. Or it can be in one of the stations, and lucky for it, it's not waiting in the queue, it's actually receiving service. So you can call that it's being at the head of the queue, and it's receiving service. Okay, so if it's an amusement park, it's actually engaging in the ride or whatever it is. Or it can be in one of the stations, and it was receiving service, but it's partially served, but life's tough and the server broke down. So it's waiting for the server to be repaired so it can continue to receive service. Or it can be out of the system after leaving. Okay, so keep in mind that with the exception of the final task, your simulation should actually it should not have entities of individual jobs. So even though you think about the system as having individual jobs, your simulation state, when you capture the state of a certain node, that node does not just have well, objects that mark individual customers, right? Or individual jobs with L equals 1, 2, 3, etc. But it only counts how many jobs are there, and it knows if the server is on and off, and it broken or not, yes, and it knows if the job in service, how long it has left. Okay, this is a discrete event simulation, but time is continuous, okay? And it's driven by randomness because jobs arrive to the system according to random processes and traverse between the stations as we described now, and they also get random service, etc. So there's a whole lot of randomness happening in the system. Still, we're going to report mean values mostly, and these will be steady state mean also. So steady state means that you run the simulation for a long duration of time, long simulated time, and you take a time average of them. Okay. All right, so here are some parameters. Each station has its own service rate. So that's this number. The service rate is like the inverse of the mean expected time it takes to serve a single job. Or you can think of it, if the service rate is mu I, and say you work for 1,000 hours, so mu I times 1,000 is the expected number of jobs that would be served if the server works uninterrupted. Okay. And each station has a queue. That queue has infinite capacity. 2 years ago, we had a similar variant of this project. There were finite capacity queues, so when jobs arrived and the queue was full, they had to go elsewhere. So no limit on the number of jobs in the queue. So queuing space is not a problem. And jobs are served one after the other, okay, with this mean, okay? And basically, when a job comes and it starts its service, that's when it kind of you generate its random duration. Alternatively, it could have been kind of written elsewhere before, but basically, the job arrives to server I, you get a random duration with mean mu I inverse. Okay, and that duration is independent of anything else. The thing is that at any given time, the server can be an on state, and that's not broken down, or off state, that's broken down. And when the server breaks down, that's on to off. If it's actually serving a job, then the job just freezes in place and waits until the server is fixed. That's when it goes from off back to on. And when it's fixed, the server continues. And just keep in mind that this mean mu I inverse does not count this off time. So the mean is a mean of the uninterrupted time. When a job arrives to station I, if the server is free, and this means that there's no jobs in the buffer, and if it's also not in broken down off, so it's not an off state, then it immediately starts service. So it's kind of coming to an empty server, great, you start service. Okay. But if it's busy or broken down, then it queues, it waits. Okay, if it's only one there and it's broken down, it just waits at the head of the queue. Otherwise, it waits behind other people. Okay. And jobs can arrive either after finishing service someplace else, so that's like an internal movement, or directly from the outside world. So let's see how they arrive from the outside world. So the rate of arrival of jobs to nodes from the outside world is alpha I to node I. And note alpha I can be 0. That means nodes that no jobs come from the outside world. So if alpha I is positive, the mean duration between arrivals is the inverse of alpha I. And we'll take the times of inter-arrival to be exponentially distributed. And since we're dealing with gamma distribution, we'll also tell you the exponential distribution is a gamma distribution with squared coefficient of variation of 1. Squared coefficient of variation is the variance divided by the mean squared. So this means that the external arrival processes are actually something called Poisson processes. You don't need to worry about this too much, not at all actually, but if you know what a Poisson process is, then great. Okay. But basically, you take node I. If alpha I is 0, don't worry about it. It never has arrivals from the outside world. If alpha I is positive, then there are these external arrivals that just happen one after another, with the time between arrival being exponentially distributed. Now, as for the duration of the service times, so we'll take them to be slightly more complex than just exponentially distributed. They're going to be gamma distributed, and the ratio of the mean and the variance sorry, that's the ratio of the variance and the mean. I'll change this. That's the ratio of the variance and mean. That's a square. It's a variance of the mean squared, actually. That's squared coefficient of variation. And that's going to be CS, okay? So if CS is 0, that's actually completely deterministic. So the variance is 0, okay? And if CS is 1, that's actually an exponential random variable. And if CS is like 0.1, there's not too much variability there. But if CS is like 3 or 4, that's quite highly variable. So CS is a measure of variability. Now, if the network is not generalized, it's just a Jackson network, and if it doesn't have breakdowns, then, well, if it's not generalized, then CS equals 1. Okay, and for that, there's actually closed form formulas that you're going to use to test it. But if CS is not 1, then there's no real closed form formulas for the performance of this network. I'll explain what that means in a couple of minutes. Okay, and then you actually want to do the simulation. So it's really kind of needed, the simulation engine, if you want to understand the nature of this stochastic model. Now, when a job completes service at some node, at some station, at some server, yes, then it either leaves the system immediately or it immediately moves to another buffer. This immediately means that we don't account for the time of moving between server to server. And the choice of the destination of where to go is according to some routing matrix P. So what does P have? So the ith row in the j's column is a probability of leaving from station I and going to station j. So each row of the matrix P is almost a probability distribution. It's something a bit less than probability distribution because the complement of the row, this is a complement of the row, is a probability of actually leaving the system. You'll see examples in a second. So when you draw from the row of this matrix P, of draw, I mean, you want to sample, you want to see where does my job go next, you can use the sample function from StatsBase. For example, that was in one of the questions in Big Homework. Okay, so how does breakdown and repair work? So you have these two parameters. They're not per server, they're for the whole system, just to simplify things. And they're gamma 1 and gamma 2. So the system moves between being an off state, on state, off state, on state, off state, on state. Ideally, on states would be much longer than off states, right? I mean, we don't want it to be broken down too much. Okay. So off durations are exponentially distributed with this mean, and on durations are exponentially distributed with this mean, and the inverse of those means, we call them rates. And these on and off states are completely not influenced by the number of jobs, by the server being used or not, by anything else. They just happen exogenously. Okay. An important quantity is R here, and that is the long-term proportion of being an on state. Okay. So that's the mean of being on divided by the sum of the means, or you can represent it this way too. You can also consider the case R equals 1 if you would take like gamma 1 to go 0, and that means that you've got infinitely slow breakdown rate. Okay, so that means that the time between going off to on kind of goes to infinity. Okay, so R equals 1 means you actually don't have breakdowns. R less than 1 means that you have breakdowns. So R still needs to be greater than 0. So it's also important to know that the duration of a job in service is drawn at the moment it enters service. So if for a specific job, the duration, say X, so a job just arrived to service, it's then drawn. And what is it drawn? It's drawn according to this random variable with mean gamma distributed with mean mu I and squared coefficient variation CS. Okay. So if it has this duration X, okay, then it only leaves the service when it's been X units in on. So it can say the time is 17.3. It works for a bit, then the server breaks down, it pauses, then it works more until you reach 17.3. Okay, that is, the service pauses when the server is off. That kind of makes sense, right? So what are the parameters of this network? So you got the L is just a dimension of the network. You got the external arrival rates, okay? You've got the service rates. You've got the routing matrix, okay? So this is a substochastic matrix. Each row potentially sums up to 1, but often to less than 1, okay? You've got the squared coefficient of variation of the service processes. Okay, that's the same for everything. And you've got these on-off parameters, gamma 1, gamma 2, which also determine R, which say how many breakdowns you have. Here's a tip. This bit of code, which we call rate CSV gamma, may help you generate gamma distributed random variables with a desired rate and squared coefficient of variation. So all we did with this code, we just gave you some code here, which basically, if you give a rate, so that's like a mu, okay? And you give it a desired SCV, that's like a CS. Okay, so for example, if you had mu 1.3 and CS 2.1, this thing is going to generate, it's going to create a distribution object. It just constructs a gamma distribution object, and that it does it with, these are the parameters of the gamma distribution as they are in the distributions package. Okay. And the mean of this guy is going to be, the rate is going to be the inverse of 1.3. Okay. And the squared coefficient of variation, okay, so the variance divided by mean squared is going to be, as you specify, 2.1. Okay, and you can see this here either via just a theoretical calculation, so using the method mean and var on this gamma struct, okay, or doing Monte Carlo, so we generate 1 million of these guys and we do the sample mean and the sample variance and we see these things. All right, so that's a useful little helper function, one-line function that can just help you create those guys. Now, arrival rates to nodes and traffic equations. So just in order for you to simulate, so everything you need to know to simulate this thing is up here. Okay, that's kind of the specification of the model, but we just wanted to give you just a bit more info and some supporting code that would make sure that we simulate within parameters that are reasonable. Now, what do I mean by parameters being reasonable? Well, in this case, we want to do simulations that when you simulate them in the long run, and we want to study systems that when you look at them in the long run, there's this steady state type behavior. So the system doesn't explode, the queues don't grow to infinity. So basically the system is stable. So for this, we just need a bit more math here, but you don't need to dig too much into this math. But let's understand it anyway. So arrival rates to nodes and traffic equations. Jobs arrive to nodes either from outside or internally after being routed to a node, okay? So if you basically call AIT the number of arrivals into a node, either from the outside world or from other nodes, and if you do AIT, right, so AIT is just a non-decreasing function, right? So if you do AI of 1 million, it's after 1 million time units, how many jobs have arrived, okay? If you divide that by 1 million, or just, ideally just take limit t to infinity, you get this thing lambda I, and this is what you call the rate. This is actually the rate of arrival to a node, right? The whole point is that the rate of arrival to a node is not just things that arrive from the outside, it's also things that arrive from the inside. Now, you can measure this quantity via simulation, as you will do for testing, but it can also be computed directly via a matrix equation. And this is a matrix equation. Before the matrix equation, let's actually look at the scaling representation. Okay, so the rate of arrivals to node I is the rate of arrivals from outside plus all arrivals from other nodes J multiplied or taking their arrival rate lambda J, and then multiplying that by the probability of going from J to I. Okay. Now, if you represent this for I going 1 to L and you write it in matrix form, you actually get this matrix equation. Lambda equals P transpose lambda. It's P transpose because you're kind of multiplying. If you take lambda as a column, you're doing it like that. Okay. Plus alpha, well, that's a vector, and that's a vector, and that's a vector. Now, there was an assumption here. There was an assumption that the rate of going in is the rate of going out. And that assumption is satisfied as long as lambda is less than R mu. R was this kind of breakdown coefficient, right? Well, proportion of time we're being on. So if just R is 1 for a second, so ignore R. So you just think of lambda is less than mu. So the thing is, these steady state equations only hold when lambda is less than mu. Otherwise, nodes are just going to fill up and the queues will grow. And we don't deal with that case. Okay. So if that is the case, then you can actually take this equation and so you stick here an identity matrix and move things to the other side, and you multiply by the inverse of this thing, and this thing is going to have an inverse because it has a spectral radius less than 1, but that's a detail that's not so important. You can actually solve for lambda. So using kind of this matrix expression, you actually have the effective arrival rates to nodes. Okay. Now, with this effective arrival rate, it's also, we can actually define the load of a node. So what's the load of a node? The load of a node is the ratio of the arrivals to the service rate. Okay. Now, systems will be stable, and that's the only case when we're going to deal with them, when rho I is going to be less than 1 for all i's. Okay. And we can also denote rho star as like the most unstable node. That's a bottleneck node. That's a node that's most busy in a sense. So if this was too fast or above your head, well, first of all, read it anyway, but you don't need to worry about it too much to actually move forward and do what we're about to see. So what does queuing theory tell us? So queuing theory is a field of applied probability. You get into this if you do stat 3004 at UQ, but of course in other places you study it elsewhere, etc. And you start with Markov chains and you move to more complicated things, but that's the whole field. All right. So in general, it's known that as the load grows, okay, and then the load grows, but we're still going to keep it less than 1, okay, then individual queues, there's more congestion. And why is that? That's kind of because of just kind of jobs don't get time to get served, and it's kind of like think of when you fill up your sink with water, and water is draining through the sink, but there's still some movement of water there, and there's some water up in the sink. So that's kind of what happens at this discrete level with queues. Okay. So that's more rho I. So the load of the node grows. We're going to get bigger queues. Now, what do I mean bigger queues? Queues fluctuate. There's nobody in the queue, one person, two people, 3 jobs, 4 jobs, 4 jobs, etc., 3, etc. The move, But if you take it over a time average, you look at the steady state number of jobs in the queue, that steady state mean is going to grow, or that distribution will generally be higher. It will have higher descriptors, etc. So further is rho star. Rho star was a bottleneck, grows. Then the general congestion in the network grows. So since we consider rho star strictly less than 1, we only focus on networks that are stable. Right? But when you're close to one example with 0.95, then you're going to get some pretty big queues happening. Okay. Also, we know in queuing theory that service time variability positively affects queue sizes. So you have highly deterministic jobs, you have less variability than when CS is 3.0, etc. And similarly with the exponential cases, someplace in the middle. Okay. Now, this paragraph is important. In the case that CS equals 1, and you're actually speaking about exponential service times, and when you don't have breakdowns, so Jackson's results from the late 50s and early 60s can actually, he proved that the steady state queue length of each queue has a geometric distribution with support 0, 1, 2, etc. And the mean of this distribution is rho I divided by 1 minus rho I. So this is incredible. So we actually know that if CS equals 1, and leave the breakdowns aside for a second, okay, and all of the rows are less than 1, so rho star is less than 1, so the system is stable, okay, and it's a complicated stochastic process. There are many jobs and the queues are moving throughout, but when you look at an individual queue in steady state, this is going to be the mean number of jobs in the queue. Okay, so here's a plot of this function. This is rho, and this is the mean steady state queue length for an individual node. Okay. Now, if you sum up all the nodes, you'd also get the mean steady state in the system. Okay, so you can do this rho for different rho i's. You can look at if there are L nodes, you'd sum them up, you'd get this type of profile. So a lightly loaded system doesn't have too many jobs in the queue in steady state, mean, and as rho goes to 1, there's an asymptote here, and this thing explodes. Okay. Now, for the case CS not equals 1, you don't have these nice, beautiful curves analytically. There's not a simple expression like that. There's only approximations, etc. And a lot of modern queuing theory deals with that, but we're not going to worry about that. So one of the main goals of the project is to quantify the effect of the squared coefficient of variation on the mean queue size, and also the effect of breakdowns. And we'll see that as there are more breakdowns, you also add variability. And also, so basically, I'm going to now draw on the screen for a second. Let's see if this works. So this, say, was CS equals 1. Okay, this is with CS equals 1. This is for an individual queue, but you can do this for the whole network. And maybe you'll have for CS equals 3, a curve that's like this, for example. Okay, CS equals 3. Okay. And similarly, this was for CS equals 1, this black curve. Okay, sorry about the color. And for R equals 1, you don't have breakdowns. But if you do breakdowns, say if you still keep CS equals 1, but you do breakdowns, you'll also go higher and you'll also get something like this. Okay, so this can be for, say, R equals, sorry, I cross curves, etc., but that doesn't matter, 0.8, for example. Okay. So as rho increases in terms of breakdowns, because breakdowns also should add variability to the system. So seeing these things that I'm postulating now in your simulation is one of the goals. You have specific tasks for that. You'll see them in a sec, or in a couple of secs. Okay. Here's a tip. The tasks below are not expected to look at it per node, but the whole network. So create a superposition of these guys, and you'll get for the whole network. Now, we actually give you example network. We don't give you a complete example code, complete project, but you actually have bits of code in the lectures that you can copy and adjust and adapt once you understand them, but you need to actually compose them into a project. But we do give you these example networks, and we want you to work with these networks. So a network is a network parameters object, okay? We use here the @with key W macro from parameters.jl, and that just allows you to have a nice constructor for this, so you can do kind of keyword argument constructions for this. Okay, so what does a network have? It has L, it has a arrival rate vector, it has a service rate vector, it has a routing matrix, it has a squared coefficient of variation, okay, and it has these two parameters for the breakdown rate and the rate of repair. Notice that we started with the rate of breakdown to be very low, so gamma 1 is effectively 0, okay? And that means that actually there are almost no breakdowns, okay? Now, we give you this nice function, this one-line function, service capacity. It gets network parameters, and it's actually going to just return this vector mu multiplied by this thing, which is basically R, okay? So this is going to say, what's the service capacity? It's just a useful function. It's just R times mu. Okay, that's the denominator of this going, if you like. All right, but it's a vector. Okay, and then here's some example networks. So you get a network with, like, scenario 1, you've got 3 nodes. And just to understand this network, jobs finish at node 1. They always move to node 2. They finish at node 2. They always move to node 3. They finish at node 3. Where did they move? With probability 1, they move to the outside world. Why do I say that? Because this thing, so 1 minus the sum of this, 1 minus all of zeros is 1. So with probability 1, they move to, you could have called it node 4 or node 0, but they move outside. Okay? All right. Here's another scenario. Okay, now here we use this @set. That's from the accessors package. That just allows you to create a copy of scenario 1 where you've modified, in this case, the matrix P. Okay, structs in Julia by default are immutable, right? So you're creating kind of a new one when you've made a modification. That's what the accessor does. So we keep the same parameters, L equals 3, the same external arrival rates, the same service rates. But here, let's see, they finish at node 1, they go to node 2. They finish in node 2, they go to node 3. But they finish in node 3 with probability 0.3, they go back to node 1. With a complement with probability 0.7, they leave. Here's another example. Here's a network of 5 queues. They finish at node 1, they either go to node 2 or leave. They finish in node 2, they either go to node 3 and leave. And it goes to this, like this in a ring, even like that. In node 5, they finish in node 5, they either go to node 1 or they leave with probability 20%. And here's some crazy network. There's, well, not crazy, but there's 100 nodes here. It's kind of a large arbitrary network. So good to test on this one too. If you keep the same seed, you get the same network all the time. So there's 100 nodes, and here we're just constructing the substochastic matrix. Okay. So here's already task 1. Task 1 says, okay, you got a big story. Now think about modeling assumptions. I suggest to do this task in 2 ways. First of all, just do it as you start the project. Think about modeling assumptions, write a paragraph or 2. Say what here fits and describes models dream world and what not. I mean, big things, for example, in dream world, you might walk between nodes. Or in dream world, you probably have multiple customers being served at a time. Okay, unless it's one of these highly, very not effective rides. I think they're all not effective. It's just not fun, this dream world. But if you like it, great. Okay. But then after you write this thing, then listen to Anna Foglin's lecture towards the end of your project duration and maybe just refine it just a bit. Okay. Here's task 2. This task 2, you see a lot of text and code here, but it's actually not hard either. All your work is in task 3, pretty much. Well, a good part of your work. So task 2, what are you supposed to do? So we're giving you 2 functions, maximal alpha scaling and set scenario. What these functions do is they get one of these network scenarios, or another one if you'd like, but it's fine if you just work with these 4 scenarios. So you can copy paste this into your project. Okay. And they actually adjust the arrival rate such that the load on the network, okay, the row star, okay, this, where is the load? This row star is exactly as you would like, all right? And let's see this in action. So the function maximal alpha scaling actually tells you, I give you a network, or you give the function a network, it's actually going to return how much you can scale alpha by, maybe increase or decrease. So you take the vector of alphas and you just stretch it. You multiply by a scalar such that you'd still be stable. Okay. So here's, for example, max scalings apply to the 4 scenarios. So we just use a broadcasting operator to apply it for the 4 scenarios and just round to 3 different digits. So it says, like, the first scenario you can scale by 2.0, the second scenario you can scale by 1.4, and the third scenario by 0.2, and etc. Now, how do we interpret, for example, this 2.0? Let's go to this first scenario. This 2.0 means that you can multiply this by up to 2.0 and still stay stable. Staying stable means that these conditions, which I said here, that lambda is less than r mu, is holds, okay? And then these traffic equations holds and your network doesn't explode, okay? That's what this maximal alpha scaling does. You don't need to touch these functions. You can, for the joy of it, understand how they work. It's not too complicated. They basically just solve the traffic equations and see. Okay. All right. Now, here's a second function, and this function would take a network and it would adjust it to have a desired row star. And in the way it also adjusted to have a desired square coefficient of variation. So it just changes the square coefficient of variation because by default it's at 1.0. So it changes it. Okay. And it changes the R. Okay. So if you don't do anything, it keeps R at 1.0. Otherwise, it actually changes R and you can make it less. Okay. So here, let's look at, for example, scenario 2 and say we want, in scenario 2, we want to be at rho star equals 0.7. So what does it mean? It means we want to take the scenario 2, which has these parameters, but it also has these, okay? And we now want to adjust, we want to scale lambda such that the load, the maximal load of the bottleneck node is at 0.7, okay? That's what we're going to do in scenario 2. What is it? Here. And we're also going to set the square coefficient variation to be 2.4. The third parameter, R, we're not touching it, so it has a default of 1.9. So after we do the set scenario, the adjusted alpha is going to be this. Before, it was something else. Alpha was not like this. It was rather 0.5 dissonance. But now it's going to be a bit less than 0.5, like 0.4900. Okay, so we scaled it as follows. Now we can actually check this. So this is just code that just checks. So we're actually checking these traffic equations. We're doing I minus P transposed. This is a backslash operator. Yeah, so it's solving the alpha vector. You could have done it with an inverse as well. And then you get rho, and then you get rho star, and you see that rho star is 0.7. So that works. Okay, now if say further to that, so just like we had before, we also added R equals 0.5, okay? So now the adjusted gamma 1 and gamma 2 are going to be 1 and 1. So before, by default, they were not 1 and 1. They were like almost 0 and 1, okay? So there were almost no breakdowns. But now you got breakdown and repair at equal proportions, okay? And you're still going to get the desired rho star of 0.7, but now, you know, the alpha was reduced. Why? Because your system has all nodes are broken down half of the time. So your arrival rate was effectively halved, okay, from what it was here. Okay. So your task is just now to take CS equals 1 and R equals 1.0 and create 4 plots for the total steady state mean Q length as a function of rho star. So it's very easy, okay? It's more about just understanding what's here. So how do you create the total state mean Q length? All you do is you just sum up these guys, okay? And that's according to this formula. Now, this is a theoretical formula, but later down, you'll compare that with simulation. Okay, so you sum up over all nodes I, and you do a superposition of these, and that's the steady state mean Q length. Okay, so that's what you do in this task. All right, task 3. So this is 40 points. There are 100 points in the project. This is your task, okay? This is your simulation engine. It's based on Q state supporting breakdown and repair. So create the simulation engine, and you're going to have some function simnet, which that's your engine. You're going to give it its network. You're going to give it a max time that's up until when to simulate. You're going to give it some warm-up time. So warm-up time means that you simulate, but you don't record statistics up until this time. You're going to get some seed, and this thing is just going to return the estimated Q length. Okay. So this is really your discrete event simulation. Now the thing is that in the lectures now in unit 6, you actually get a discrete event simulation engine. So you have an example of how to do this, and Andy will build with you this lecture with a few examples on how to do this. So I would get to task 3 only after you followed the lectures dealing with discrete event simulation, but doing task 2 and task 1 and getting acquainted with things, starting to think about task 3 is a thing to do probably right now, the minute you're watching this video. Well, maybe not the minute, but the minute after. All right, so important that this simulation does not keep individual customer state. It only keeps the number of jobs in each queue, and if each server is on or off, okay, broken, working or broken down, and if it's off, how much time it has until it's going to be on, right? And this is a discrete event simulation engine where, you know, events can happen, and every time there's a next event happening, etc. The practical should also be useful for this. Now, there's a bunch of tests that you can do here. to see that this thing actually makes sense. And what you're going to do with the test is you're going to compare it to theoretical results, you're going to compare to flow rates, you're going to look at the long-time proportion the server is on, that's not too complicated, and you're also going to do some qualitative tests. So once, of course, this task is going to, your code might span multiple files. This is really the meat. Well, I'm a vegetarian, but this is really the fake meat of this project. All right. Okay. So now when you get to task 4, you're actually using this nice thing you did in task 3. And frankly, it might be an iterative process where you move between 3 and 4. In task 4, you're going to be a bit of a queuing scientist. You're going to check how CS, the square coefficient variation, and R has an effective queue size. So basically, what we want to see here are curves where you have rho star that goes from 0 to 1, okay? And as rho star increases, it'll get towards 1, queues grow. But when CS is bigger, the whole curve shifts up. And when R is smaller, the whole curve shifts up as well, okay? And you're going to use, so it basically means running this guy that you created here many times. Just a tip, don't start with very heavy simulations and with a long time, start with short simulations just to see that everything works. So you can do this by not waiting too long for the computer, adjusting, tweaking until you get the right plots. Now, your final task is actually quite a lot more coding and design, but so that's not captured in this few points. It's just 10 points, okay? But that's kind of a differentiated task. So here you're going to create something that I'll call SimNet customers. So this is a simulation engine, and you also have example like that in the lecture. This is a simulation engine that actually keeps track of individual customers and knows where customers are. So it knows if a customer is here or there, and there. And the reason it does this is when a customer enters the system, you start their sojourn time, and when a customer leaves the system, you finish their sojourn time, and then you actually can collect the sojourn time of these customers, and you can actually know something about the distribution of the sojourn times. In this case, estimate the Q1 and the Q3, the quartiles of this distribution, okay? And a bit more like we say here. This is your 5th task. Okay, that's the project. Hope it's not overwhelming. Use the consultation hours, use the support practicals, use your practicals, ask Andy a lot of questions, and me, and good luck. Bye-bye.